Hello, it's Keith here, and this is lesson 7 of the Photon series of my 6502 assembly programming tutorials, and today we're looking at the VIC-20. Well, what is Photon? Well, it's a simple little Tron clone, and it's really there as an example on drawing pixels to the screen. Now, you can see here we've got the game, and the problem of drawing pixels to the screen was indeed a bit of a problem for the VIC-20. Now, the VIC-20 only has definable characters. It doesn't really have pixels as such. But one YouTube commenter, I don't tend to read the comments, but sometimes I do, and luckily someone pointed out the VIC-20 has a tricky mode where the characters, rather than being 8x8, are actually 8x16, and this allows us to actually create a fairly large bitmap screen that you can see here. We're going to go into the technicalities of it in a moment, but first I just want to discuss the functionality of the game. Now you can see that and its CPU just went past that yellow object and it turned green, and if I get too close to this yellow one, you can see it turns purple, and that's because there's only one color attribute per 8x16 block. Now the game itself has a left and right turn. If I press left and hold, it won't turn again until I release and press again, and that's so I don't accidentally crash into myself. Also, if I press fire, I will move a bit faster, and that's known as boost mode. We're going to discuss how those work in just a moment, because you will see those in the code. But as I say, the most interesting thing is this 8x16 mode and how we can use it to simulate a bitmap screen, and the bitmap screen itself is 160 by 192, which is actually pretty respectable. So well done, VIC-20. Okay, so let's go over to the source code and let's take a look. Okay, here it is. So the game is built as a ROM file, so I didn't want to have to deal with very tight memory limitations. I don't know if it would have been possible, or I wasn't going to try. We're just going to work with a ROM cartridge, which is the easiest way of doing things, so that's what we've done. Okay, so we're in a ROM cartridge. You can see the header just here, and we are defining some variables for our game. Now, the memory for the game needs about 128 bytes or so, not very many, but it needs a few bytes of RAM, so we're defining it as memory address 200 in hexadecimal. We are also defining the screen size, 160 by 192, and we're using the smaller scale for the scalable objects like the title screen, because they are really designed for 256 by 192, so they wouldn't fit on 160. So that's what we're doing there, and we're defining the 4 game colors. Now, black is the background and the other objects are colored, and we're defining the color attributes that are going to be used for those, and we'll see those later on. And next, what we're doing here is we're initializing the screen with the settings we're going to be using, and you can see the settings down here. Now, they are a little bit tricky. We are enabling the double size option with bit 0 of memory address 9003 here. We're also relocating the screen because we're going to be using basically all of the characters we're nearly redefining. We're defining the screen base at memory address hexadecimal 1000 and the character base at the same address. Now, this basically means that the first 16 characters aren't actually going to be usable because they'll be overlapped by the actual tile map, if you will, with the character selection for the screen characters. So that's the way it is. It's not really a problem because we don't need them. Everything is pixels, including the font and things, so that's going to be okay. But these are the settings we're using, and that's what we are setting up just here. Now, the way we do things is we actually define the entire screen to show consecutive characters. We're treating it as a tile map. So we are using this fill area with tiles. We're starting at character 16, and we are defining 20 characters along the screen and 12 down the screen, and that means we're using a total of 240 characters. And as I say, we're starting at 16 because I think 15 of those first 16 are overlapped by the data we're drawing just here. So that's important. Okay, so that's got our screen set up there, and then we are clearing the game memory here and showing the title screen. Now, we're going to come back to the other screen options in a moment, but next we're going to discuss the main game code. Now, we won't be discussing reading the joystick and things like that. They were covered in the Simple series. They were covered in YQuest. We're not covering them again. So if you need to see those, please have a look at those other episodes. We're just going to look at these new graphics options in this one. So we've got this game tick thing here. Now, the boost mode means the player moves at twice the speed, and so to do this we have a tick, and the player will either move every tick in boost mode or every other tick in normal speed. We've got a delay here, and this is different in boost mode, and that's not to make the game faster. It's actually to compensate for redrawing the font of the boost counter in the corner because it's a bit slow. The vector font's a bit slow, but it is quite convenient because we don't need to worry about 2 drawing routines. So that's what's going on there. We're reading in our controls here, and we're checking if no keys are pressed, and if no keys are pressed, we're clearing the key timeout. And this is used, as I said before, if you press left, you have to release left and then press it again to move left twice. And this is clearing that timeout there, and that's allowing us to press a key again. So this is our delay loop here, and it's also our key reading. And then once we get to here, we're checking if the key timeout is 0. If it's not 0, then we still can't move. So we're skipping over the joystick changes here. We're not processing the joystick in that case. Next, what we're doing is we're setting boost to 1, which turns it off, and then we're going to process the directions. We load 0 page entry IX with the player acceleration. Now this is because set player direction will use that to turn the player if the player has turned. The same routine can do the CPU, you see. Then we're checking the left and right directions on the joypad, and we are decreasing or increasing the player direction. It works in 90-degree rotation, so up, left, down, right, or vice versa. So going around in 90-degree rotations there. So that's what these are doing, and we are setting the key timeout if left or right are pressed. We're then checking the joystick. If the joystick fire is pressed and boost power is not 0, then we're turning boost on, and that's going to make the player speed up. And all of that's handled by the handle player routine here, and the CPU versions are done by handle CPU. That's all of the game logic of has the player collided into things, are they dead, that kind of stuff. So that's the main loop. It's fairly simple, and that's the way we want it because the rest is all in the multi-platform code. Okay, we've got the fill area with tiles here, which is filling the characters for the visible screen. We're not going to cover that. That was done in the simple series in the bitmap example. It's exactly the same. It's just consecutively setting characters onto the screen. Here's our PSET routine here. Here's our calculation routine for PSET, and here's our point. But first, I want to discuss the CLS routine. Okay, here it is. And we're basically clearing the entire character definitions. So the character definition for character 16 is a hexadecimal 1100 here. And we are going to clear those. And we are clearing 192 lines and 20 characters across. And it's 1 byte per line of each character, so that's what we're doing there. So that's clearing the screen, and we're going to then change those pixels when we want to plot something to the screen, and a PSET command will do that. Now in theory this uses a 16-bit value in AB, but this system doesn't need that. That's for the 320 pixel wide screens. So this one we're just using 0 page B as our X position. What we're doing first is we're checking if it's negative, and the reason for that is the boost counter is actually drawn starting slightly off the screen, and that was causing horrendous glitching on these systems, so we don't want to do that. So we're just checking if we're being told to draw it off screen and returning if we are. And then what we're doing next here is we are going to work out the memory address of the pixel within a character definition that we want to change. Now each character definition is 16 lines, so 16 bytes, and each line contains 8 pixels. And so we're going to need to take one of those pixels, we're going to need to either make it black to turn it off or make it coloured to turn it on. And we've got a mask to do that for us. So this mask here is all of the possible pixel positions from 0 to 7 within a byte and the bit that affects them, and it's very logical in this case. So we're loading that in according to the bottom 3 bits, 0 to 7, of the X coordinate here, and then we're pushing that onto the stack here and we're getting it back there. We're using then this calc VRAM address, and this is calculating the byte position of the definition of the line of the character that the pixel we want to change occurs in, and that's so that we can change that pixel. We're then getting back that masks for the pixel we want to change here, and we're storing it in 0 page entry B. We're then flipping all the bits, and so now it's a mask for the pixels that we want to keep, the other 7 pixels. And we're storing that in C here. We're then loading in the pixel from the screen at the address that we calculated here based on the XY position of the pixel we want to change. We're keeping the pixels we want to keep, and then we're checking the color we want to use. If the color's 0, then we're going to just write it straight back to the screen because the pixel has been removed that we want to change. It's now black. If it's not going to be black though, we need to OR in the mask that we read straight out of the pixel mask, and that's going to set it to colored. Now what colored it's going to be set to is going to be defined in just a moment. We're then going to store that back to the memory of the character definitions that make up the screen definition there, and then what we're going to do is we're going to use get VDP screen pos, which is the function we used in the simple series, and that's going to calculate the memory address of the character block that is containing the pixel that we just changed. Now what we then do is we add hexadecimal 8400, and that offsets us to memory address 9400, the relative offset for the character we just changed, and that's the color information for that character. The reason we're adding 8400 is because this is returning based on the 1000 screen base of the character blocks. So that's now the color, and we're then just storing the color that we wanted to change to, and we're pulling that off the stack from here. It's Z0 page entry D, that's the color attribute, and the color attributes are one of these. So these are the colors, and so the block that we just changed the pixel of is now being colored in that way, and that's why when our player goes past one of the blocks of the background, it changes color, because this is updating the color based on the latest draw to that block. Okay, so that's how we're doing the pixel, but we had that calculate VRAM address, which was doing a lot of the work. Here it is. So the mathematics gets a little bit tricky here, so we're going to try and go through it. Now, the bottom 3 bits of the X position are 0 to 7, and that's within the single character line. So we're going to ignore those here. We're going to take these bits here, and we're going to work out the position of that. Now, we need to multiply this by 16 because consecutive bytes in memory go down the 16 line character block and then they jump back up. So we take this, we rotate it to the left, and that is the first part of our memory address, because we've effectively multiplied the top 5 bits of the X position by 16 there, and that is the character block position for the X position, ignoring the bottom 3 bits because those are being done by this pixel mask. What we need to do next then is we are going to add the tile definition base. Memory address 1000 is the tile base, but we're starting at character 16, so it's 1100, so we're adding hexadecimal 11 here. And we then need to work out the Y position. Now, as I say, there are 16 lines within each character block, so we're taking the bottom 4 bits, 0 to 15, of the Y position, and we're adding those as is because they're consecutive in memory. But what we need to do next is take the remaining 4 bits of the Y position, and we're effectively going to multiply those by 20 times 16. Why 20 times 16? Well, there's 16 lines per character block, and there are 20 character blocks on each line. So to work out which strip of the screen we need, we multiply by 20 times 16. And the way we're doing this, well, we've already effectively multiplied that by 16 because we've ignored these bits here, but we still need to multiply by 20, and we do that by consecutive bit shifts. We're effectively shifting to the times 16 position and then shifting to the times 4 position, and that effectively multiplies us by 20. So that's how we're calculating our VRAM address there. Now, that's how we draw our pixels, but we've also got this point command here, and this is how we read them back in. Now, our game only cares if a point is black or not black, but that's what we're doing here. We're taking the pixel mask again, getting the screen position using calc VRAM address, and we're masking the pixel, and we're then seeing if it's 0 or non-zero. If it's non-zero, we're returning a 1. If it's a 0, we're returning a 0 here. And that's how we're testing the pixels to see if we've collided with the enemy or the enemy's collided with us, and so on and so forth. We've got get VDP screen pos here. This is working in character blocks, so the shifts are a little bit simpler. As I say, you can see all of that in the simple series, and we've got the reading in from the joypad here, and again, that's all been covered before in the simple series. So there we go. I just think this worked surprisingly well. The VIC-20 is it's a system I didn't know about before I started doing these tutorials. It's not one I've got any particular experience with, and I had struggled up to this point to really imagine how I could make anything particularly visually effective in it because of the limited character blocks and things. But being able to do all of the pixels on the screen like this was quite a impressive surprise to me, because I hadn't really thought it was capable of anything with this kind of fidelity, so I was quite impressed with it. Anyway, as always, you can go to my website, you can download the source code, and you can do whatever you want with it, and maybe you can make it better. I'm sure you can. This game was, I'm not going to lie, this game was a bit of a rush because I needed to get it out to cover it in the tutorials, so it's hardly the best game in the world, but I think it's an effective tutorial in how to do pixel plotting, so if it's any use to you, go ahead and download it, and hope you have some fun with it. Anyway, if you've enjoyed this video, please like the video and subscribe. If you like the videos, it recommends them to more people. And if you subscribe, well, it increases my morale, and maybe you'll get some more VIC-20 videos further down the line. Anyway, I hope you've enjoyed this. Thanks for watching. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.